Okay, I hope it's become apparent that increasing the number of rectangles decreases the amount of extra area or missing area, which means our approximation gets better and better to the true answer. So this GeoGebra document is going to quickly illustrate that point. This is a curve function. This is sine x if you're interested. And the Riemann sum we're doing is from 0 to pi using a right Riemann sum. And this slider bar, the value of n, will increase the number of rectangles to be whatever we like it to be. Down here in red is the area approximation so far. So far n is equal to 3. You only see two rectangles because the third one actually has a height of 0, so you don't see it drawn. Now, I can either type in different values of n to change the number of rectangles. So for example, n equals 6. And as I do that, you'll see this number a change. Okay, so there's 6 rectangles, really 5 because the sixth one has no height, so you don't see it drawn. And what I want to do now is increase the number of rectangles. And as I do that, pay attention to this number a down here at the bottom. What you're going to see you're going to see a couple things happen. As I increase the number of rectangles, they get harder and harder to see. Okay, they're getting skinnier, and also there's less and less extra area or missing area between the rectangles and the curve. The other thing you notice is that this number a does not seem to be changing very much. Okay, the first 5 decimal places are not changing at all. And if we keep increasing the number of rectangles, we're going to get smaller and smaller changes in this area. And if we could do this forever, in other words, we could let n increase to infinity, we would actually get the true answer. So far, with 1,000 rectangles, we've got 1.99999835551, which is pretty close to 2. So I'm tempted to say that the limit would come out to be 2. But of course, this is just suggestion. We want to actually verify this by hand if we can. So what we're after is an expression that will find us the exact area between a curve and the x-axis on an interval. Okay, to do that, we're going to need a limit. But before we can use that limit, we need an expression that will be the area using n rectangles or n trapezoids. So let's go ahead and just set this up. Okay, it's not going to matter in the end whether we use a right or a left Riemann sum or midpoint Riemann sum or trapezoidal sum. So we'll just pick one and go with it. So let's do a right Riemann sum, and let's go ahead and define some parameters here. So this is a curve called f. It's just a general curve, and let's just put some boundaries on this curve. This here is the x-axis, and this will be x equals a, and this will be x equals b. Okay, so we're going to set it up for n rectangles, so we first need to know what's the width of each rectangle going to be. We're going to use equal subdivisions in this example here. So remember, last time we took the right endpoint, subtracted the left endpoint, and divided by the number of rectangles. That's how you get the width of each rectangle. And we call that symbol delta x, so that we don't have to keep writing b minus a over n. Next, we want to divide our interval into subintervals. Now, there's going to be n of these subintervals. I can't really draw n subintervals, so I'm just going to kind of symbolically draw subintervals for you. I only need to do a few because we're just going to generalize what we're doing in a second here. Okay, since I'm doing a right Riemann sum, I don't use the height at x equals a. The first height I'll do is the one at the next endpoint of a subinterval. So where is this? Okay, well this is where I started plus a delta x. That's the x value. Okay, so the height's going to be the y value at that x value. We'll get to that in a second. The next x value that gets used to determine a height is a delta x to the right of that. So that's a plus 2 delta x's. The next one after that is going to be a plus 3 delta x's. And then the final one will end us at b, but there's another way to write b in this context. It's a plus, how many of these did I need? Okay, I started with 1, so I needed to end with n of them. So I have n different widths, n different heights, and different areas in the end here. The area using n rectangles, right, will be equal to, first rectangle has a width of delta x. The first height is going to be f of this first x value, this first right endpoint, which is a plus delta x. The second area will be delta x times f of a plus 2 delta x. The third rectangle will have a width of delta x and a height of f of a plus 3 delta x. This is going to continue on, so I can put a plus with an ellipsis. And the last rectangle will have an area of delta x times f of a plus n delta x. Okay, so if I want to abbreviate that with sigma notation, then I would say I have the sigma of something that looks like delta x times f of a plus k delta x, because that k is what's increasing by 1 each time. K begins at 1 and ends at n. Okay, so this is the area using n rectangles to approximate the region between the graph of f and the x-axis on the interval a to b. We want this to be exact now, no longer an approximation. So how do we do that? The true area is going to be equal to the area of an infinite number of rectangles underneath the curve. So we need a limit as n goes to infinity. This is a neat concept. Okay, obviously you can't have infinite number of rectangles, but we can take the limit of these areas and see what number that limit approaches. So everything else stays the same. We just take the limit as n goes to infinity of this expression. And that's how we obtain the true area between a curve and the x-axis. That's the mathematical theory anyway. We won't actually be doing this by hand because we're going to learn some cool shortcuts to circumvent this process. But we'll do one example with a calculator. So let's do a specific function. Let's do f of x equals x cubed. And let's do, again, a right Riemann sum. I'll show you that it doesn't matter whether it's right or left when we do this. And let's do an interval from 1 to 3. And we're going to set it up so that the TI Nspire will do it for us. So, first of all, what's our delta x? Our delta x is going to be b minus a, 3 minus 1, over n. And n is involved in the calculation. And all we're going to do now is apply this definition up here to this specific function. So the true area between the graph of f, which is x cubed, and the x-axis between 1 and 3 is found with this expression. The limit as n goes to infinity, sigma, the sum of, right, all these rectangles areas, with a parameter starting at 1, going to n. We have defined delta x already. That's good. And then our f is x cubed, so I can still write f if I want. F of, in this case, a is 1 plus k delta x. And as long as we tell the calculator what all these symbols stand for, it will actually calculate this area. Let's take a look. Alright, so we need to tell the calculator a couple things. We need to tell the calculator that x cubed is the function that we're calling f. We need to tell the calculator that 3 minus 1 over n is delta x. We're going to call it dx because I don't have a delta symbol in the calculator. And I think we're ready to go. But there's lots of type here. So we've got to go calculus. We need to take a limit. The limit is what? N goes to infinity. Where's infinity? It's down here under the pi menu. And now inside the limit goes the sigma. K starts at 1, goes to n. And we want to do what? Delta x times f of 1 plus k times delta x. We'll do control equals, and we get 20 as an answer. So that's telling us the exact area between the graph of f and the x-axis between 1 and 3 is 20. Let me just verify real quick to you that if we did a left sum, we get the same answer because of the limit going to infinity. It doesn't matter which method we use, we're going to get the same answer. So if we did a left, we go from 0 to n minus 1, and we still get 20. And let me do one more thing for you here. Let's do a quick approximation using an exact number of rectangles. Let's say we had decided on 1,000. So in this case, 3 minus 1 divided by 1,000 would have been our delta x. So let me restore that real quick here. And we can redo the calculation and see how close that was to 20 to get an idea of how good this is. So 1 to 1,000, delta x times f of 1 plus k times delta x. And what do we get? A little bit more than 20, okay, 20.026. So the more rectangles we use, the closer we get to 20, which is the true area. Now, you might guess that it's going to be cumbersome to continue to write all these symbols if all we're talking about is an area of a region. And luckily, a German mathematician agreed with you and said, okay, instead of writing this out all the time, Let's come up with a more convenient symbol to use that's less cumbersome. So what he did was he said, okay, if this is the Greek letter S, which stands for sum, let's just write an S, but stretch it out a little bit. And since A and B were built into this formula somewhere, let's make them more explicit and put them above and below the S. So my starting place for finding area is below. My ending place is written above. This is my function that I'm finding the area under. And we've already seen before that delta x and dx can be used interchangeably. So let's replace delta x with dx. Okay? So this symbol here stands for the same thing as this, so we know what it means. Here's how you read it. The definite integral of f of x dx from x equals a to x equals b. So this elongated s is an integral symbol. The a and the b are called the limits of integration. A is the lower limit of integration. B is the upper limit of integration. We call f of x the integrand. A lot of vocabulary there, but we're going to refer to those terms quite a bit, so be familiar. We interpret this symbol, just like this, as the signed area between the graph of f and the x-axis. Okay, what that means is any area below the x-axis, okay, area below the x-axis is calculated as negative. The reason for that is how the sigma is calculating area. It's using the function's y values to determine heights of rectangles. So that's what will happen when you use integrals or sigmas. Area below the x-axis counts as negative. We know there's no such thing as negative area, but this is how it will be calculated. So we've got to be prepared to understand that. Now, as we get working with integrals instead of sigmas, there's some properties that we have to accept and be comfortable with. So the first one says that if I have the integral of a constant times a function, it's the same thing as pulling that constant out in front and then doing the integral. So if we think about this in terms of areas, this is saying that if I have the integral from 1 to 4 of 2 times the square root of x, okay, here's the square root of x times 2, here's the area from 1 to 4 in blue, and it comes out to be 9.33. I should get the same answer if I just took the area of the square root of x, which is 4.67, and multiply that by 2. And you can verify yourself that that's true. So you're allowed to pull constants out of integrals and have no penalty. Just remember to multiply your answer by that constant. You're not allowed to pull out variables, though, so be very careful you don't ever do that. The second property says that if I have the integral of a sum of 2 functions, I can make this the sum of 2 integrals. So, what does that mean? Here's the integral from 1 to 4 of the square root of x dx. That's an area. It comes out to be 4.67. And here's the integral from 1 to 4 of 1 plus sine x. That's also an area. It comes out to be 4.19. Turns out if I took the integral of the sum of those 2 functions, which would be the integral from 1 to 4 of the square root of x plus 1 plus sine x, that's also an area, and it comes out to be the same answer as if I add up these 2 areas separately. You can verify that on your own. Okay, this property I call the Hershey-Bar property. Here's what it says. It says if I take a region from A to B, find the area, and then split that region into 2 pieces, one that goes from A to C and one that goes from C to B, I should get the same answer. Just like if I take a Hershey bar, break it into 2 pieces, I should still have the same amount of chocolate. So in this case, we're saying the integral from 1 to 6 of the square root of x should be the same as the integral from 1 to 4 plus the integral from 4 to 6. In other words, the area from 1 to 4 plus the area from 4 to 6 better be the same as the area from 1 to 6. And you can verify that that's true. All right, this property here does not have a picture, but I'll draw one anyway. Okay, what does this say? This says that the area from A to B of f of x dx is equal to the negative, or the opposite of the area from B to A. Now you're thinking, wait a minute, that's the same region. A to B, B to A, what's the difference? Okay, well mathematically there is a difference. So this is the region we're talking about. The integral from A to B of f of x dx is a positive number because this area is above the x-axis and we started at A and ended at B. When this dx was determined back in the sigma stage, remember that delta x was defined to be b minus a divided by n. And this assumed that b was bigger than a. B was to the right of a. And when we define the integral, we assumed that the smaller number was the lower limit and the bigger number was the upper limit. If we reverse that, okay, now we're going to have our delta x's built in be a minus b over n, which is the opposite of b minus a over n. And so that's where that negative sign comes from, because now our delta x's would be coming out negative if we went back to the original calculations. So even though we're talking about the same area, the same region, flipping the limits gives you the opposite answer. So that's a convenient property from time to time to use. All right, so let's do an example where these properties are applied. So let's say you're told, and to tell you what, let's change, let's give A and B values. So let's say A is 2 and B is 4. So instead of using symbols, let's use actual numbers. So you're told that the integral from 2 to 4 of f of x dx is 25. So that means the area between the graph of f and the x-axis is 25. Find the value of this integral. Okay, how are we going to do that? Well, we're going to use the properties that we were given. So first thing is I see a sum under an integral sign. So that means I'm allowed to split the one integral into two. So I'm going to have the integral from 2 to 4 of 2 dx. The dx is going to go with both pieces. It will not make sense to have an integral without a dx. And the second piece will be 3 f of x dx with the same limits. Let's handle the second piece first. Another property we saw says I can take a constant out in front. That's allowed. So I have 2 to 4 of f of x dx, and the portion underlined here was given to me, right? That's equal to 25. So I have 3 times 25, or 75. What about this piece here? What is the integral from 2 to 4 of 2 dx? Well, if I interpret that as an area, that's the area from 2 to 4 underneath the curve y equals 2, or f of x equals 2. And that region is a rectangle. And we can find the area of a rectangle very easily. Okay, we just do the base, which is 4 minus 2, times the height, which is 2, and so we get 4. So as an answer, we get 79. The last thing I want to talk about is a new type of function that is now defined in terms of an integral. So naturally we call it an integral function. So this function g, what does g do? G says, I want you to calculate the integral from 1 to x of f of t dt. So g is saying, find me area. So g is an area finder. Finds the area under f starting at 1 and ending at whatever your input of x is. Okay, so g is an area finder for f, starting at x equals 1. One thing I want to point out, we changed, since this is the curve f of x, we changed the variable for f, or the input of f, to a different variable besides x. Okay, we changed it to a t. It didn't have to be a t. It could have been any letter we wanted to. But we call this a dummy variable. And the reason we use a dummy variable is so that there's no confusion to the user of the function where the input of this function is. Okay, the input of the function is here, the upper limit of integration. If we left x in here, then your user, when you say find me g of 1, for example, might think that they're supposed to plug in a 1 in for the x inside the f. And you don't want that because that means you're going to get a constant, and that's not what we want. We want this to be the function that we started with, f. So we change the variables of the integrand, there's the vocab word, to something else, so there's no confusion. But it's still the curve f of x that's shown here. Okay, what can we say about this curve, or sorry, about this function g? Okay, well, we can't do many hand calculations yet, but there's some things we can say for sure. Let's do g of 1. G of 1 would be what? That's the integral from 1 to 1 of f of t dt, or since there's no longer a problem here, I can change this back to f of x. Okay, what would this mean? That's the area that starts at 1 and ends at 1. So there's no width. So if there's no width, there's no area. So that's an easy value to calculate. We get 0. It's also another property of integrals is that the integral from number to same number will always be 0. Doesn't matter what the function is. Okay, what can we say about g of 2? Well, what is g of 2? G of 2 is the integral from 1 to 2 of f of x dx, or f of t dt. Doesn't matter because that variable is arbitrary. So that's an area from 1 to 2. So if I shade that area in, it's this area right here. What can you say about that? Well, you should definitely say that it's a positive number. Okay, my limits went from smaller to bigger, and this area is found above the x-axis, so it's going to come out to be positive as far as the area calculation is concerned. And let's do one more. Let's do g of 0. What is g of 0? That would be the integral from 1 to 0 of f of x dx. Now, there's something I don't like about that integral. The lower limit is supposed to be smaller than the upper limit, so I want to flip those. But I have to remember, if I'm going to do that, that I need to put a negative sign out in front. So this becomes the negative integral from 0 to 1 of f of x dx, and I'm going to shade that area in blue. So the integral from 0 to 1 is going to be a positive number because this area is found above the x-axis, but because of this negative sign, g of 0 is actually going to be negative. We'll work more with integral functions in class, and it's going to be a big part of our world moving forward.